All right, good morning, ladies and gentlemen. Let's rock and roll here with our review. This is for waves and sound.
Yes, it is.
Right? Okay, the velocity of a mechanical wave is determined by the medium carrying the wave.
Yeah, we demonstrated that with that slinky over there, the spring on the...
Oh, yeah. This guy right here?
Yeah.
Yep, the medium being the slinky. Okay. The source of a wave determines its amplitude, period, and frequency. Kind of like how when we did that pulse, Doctor, I can't find a pulse lab, I think it is, right? So I was the source, and I determined the frequency and the amplitude of the wave. Wavelength is the horizontal length of one cycle.
Yep.
The source and medium together interact to produce the wavelength.
You want to draw a wave on the board and show this? Because your hand is like the source going back and forth, and your feet are like the medium. Sweet.
I kind of took my pen off the board there, okay? So the source, which is like my hand, and the medium, which is, you said, the board, Mr. Boykin?
Well, it's your feet. It's how fast you're going.
Oh, because it's my velocity, right? And
Yeah.
the medium determines my velocity.
Yeah.
Together they interact to produce our wavelength, which is represented by that equation right there, which I also have on the board over here. Wait. Oh yeah. Okay, yeah. It's just written differently.
It's sulfur.
Sulfur. So wavelength is the velocity over the frequency, or V times C. Waves transfer energy.
Yep.
Yes. The energy transferred by a wave is proportional to its amplitude.
Should I demonstrate that?
We should demonstrate it.
All right. So if I send a wave, if I make a thing with a small amplitude, I'm not expending much energy. It's not doing much. But if I do the same frequency at a larger amplitude, holy smokes, that's a lot more energy.
More amplitude means we got more energy being transferred. What was the relation between the direction you were moving your hand and the direction of the wave traveled? Well, you just moved your hand.
I was moving my hand back and forth like this, and the wave was traveling that way.
Okay, so that's what we call a transverse wave. Transverse waves oscillate perpendicular to the direction of travel.
You know, that's an interesting thing. You got the waves that are still traveling through the slinky, but the piece of yarn here is oscillating perpendicular to the slinky.
Okay, so we have transverse waves, yes?
Yep.
And now we also have longitudinal waves. And a longitudinal wave oscillates parallel to the direction of travel.
Longitudinal waves are harder to see, and they work by moving your hand back and forth this way. So I move my hand back and forth that way. You've got these squeeze and stretch that go through the slinky, and that's a longitudinal wave.
Squeeze and stretch, like that. Okay. Sound is a longitudinal wave created by a vibrating object. Okay, the source, whether it be the door opening and closing, Mr. Boykin's hand moving back and forth, or a speaker moving back and forth.
Yeah.
The vibrating object pushes and pulls, like what Mr. Boykin was just talking about over there, on the medium, increasing and decreasing the pressure locally.
Did we do the window thing with the AP kids?
We did, yeah, I believe, because that was the second time I had done it with the regular kids.
Yeah, okay.
Yeah, so we actually had a question in the quiz that asked about like how sound moves through.
Yeah.
And you needed to include language that talks about the pushing and pulling, a vibrating object pushing and pulling, pressure increasing and decreasing locally. This is the most of the picture, right?
Yeah.
How do your ears work, right? And for your ears, you've got a longitudinal sound wave coming in, and it's doing work on your eardrum, which then in turns affects your inner ear, and you can hear. You hear
And
sound.
then magic happens and you hear it.
Voila! Okay, but ultimately, you've got longitudinal waves, sound waves coming in and doing work, moving your eardrum.
So the source of the sound is like when we're moving the door, and your eardrum is like the curtain we had over the window.
Exactly. Sound requires a medium. Yes. Okay, so a solid, liquid, or gas to travel. The speed of sound is determined by the restoring force of the medium carrying the sound. Oh, okay, that makes sense.
Well, if like you're in a swimming pool and somebody bangs on the side of the pool, it sounds really loud. That's because the restoring force in water is greater than the restoring force in air.
Yeah, and it's just that same idea with that squeeze and the stretch.
Yeah,
right? and with our springs, right?
Yeah, and sound travels much faster in water than in air.
Loudness is proportional to the amplitude of the sound wave.
Yeah, if you want to do that thing with your hands, you know, the small amplitude.
Oh, yeah. Okay, so yeah, if we have a small amplitude, so if we have a quiet noise, we have a small decrease and increase in pressure.
Back and forth, very small.
Now, when we have a loud sound, it's because we have a big high pressure, low pressure.
Boom, 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 boom. Yeah, yeah.
Whatever you want to call it, okay? And so that is, loudness is proportional to that amplitude, or how much my hands are moving there, okay? Sound spreads out from its point of origin in spherical wavefronts.
Yeah, it's like if you clap your hand, what direction does the sound go?
All around.
Yeah,
right?
people all over can hear it, up, down, left, right, backwards, forwards.
Mm-hmm. And okay, so horn observation. So the Doppler effect, we did this. I just kind of said that word. I'm going to get to it in a second. We just did this for regular physics today. So the horn observation, Mr. Boykin goes out, he slams on his horn as he's driving towards me, at me, and past me. And what's happening to the loudness? What's happening to the pitch here? So a sound starts somewhere and moves out like an expanding bubble.
Yeah, and the place it starts is always the same.
It's always the center of the expanding bubble, and it does not move. Should we show him that simulation, or should we go?
Oh, it's a good idea. You got it?
Mm-hmm. Yeah, it's a fair. Okay, so here we are. So when we start, okay, now I'm just gonna pause it here. So every second that goes.
Can you put the source velocity at 0?
Yeah, I can. Let's do it right there. Okay, so let's push play there. Boom, that's perfect. So now, every time this is like me clapping my hands or Mr. Boykin blaring his drum. I mean, not his drum, his horn. Right? The sound, its point of origin is right there in the center.
Goes out in a sphere.
Mm-hmm. And it expands in a sphere like.
Okay, let's go to the next slide over here.
So we've got the Doppler effect occurs when the source of sound or the listener is moving. Now we're gonna do the source of sound moving. So I'm gonna go ahead and move it up to, there we go. Okay.
And so now, even though each of those bubbles has a center, that center is moving, the source is moving.
Yeah, and so I want you guys to pay attention to the frequency, the actual frequency of the source and the wavelength of the source are set. But let's talk about the perceived frequency of the observer for right now.
Well, what's the next slide here?
Oh, okay. What do we got? If the source of the sound moves, bubbles with different centers expand. Okay, well, we can see that here, right?
Yeah,
so boom, 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 boom,
stop it. And each one of those circles.
You can see one starting right here, right?
Yeah.
So it's expanding right here, but as the source moves, more and more and more are being created and expanded.
So you have different centers that put bubbles that get closer together in the front and farther apart in the back.
That's important. Okay, so the bubble's edges get, Mr. Boykin just said, get closer together in the front, okay, when the source is moving like this, or even if you're moving, giving them a shorter wavelength and higher frequency. So notice how between here and here, here and there, there and there, there and there.
Yeah, okay. Let it go until it gets up to the observer.
Yeah.
Stop it. Right, and now, see, it's coming back more, it's coming by the observer more frequently. That's a higher frequency, and you can see that in the numbers. The horn's going at 343 hertz, and the observer is hearing 877 because the wavelength is so much shorter.
Yeah, and that's so short, so small wavelength, high frequency there.
Yeah.
Okay, now what happens when we...
Well, the next slide.
So the bubble's edges get further apart behind, giving them a longer wavelength and a lower frequency.
So let it go past the observer.
And what we see right now, it immediately changes to 213.
Stop it.
And then what happens to that wavelength?
So we've got a longer wavelength and a lower frequency. So before it's like, if you have on it's coming, it's going to be and on the way back, it's going to be excuse me.
And so, you know, Mr. Boykin always says loudness is an opinion, and it has to do with the perceived frequency.
No. Loudness is an opinion. We'll talk about loudness in a minute.
Yeah.
We need to talk about pitch right now.
Oh, pitch. Sorry. Okay, so let's go ahead and stand up here. So we hear a higher pitch as the sound approaches. Yeah, right? We just talked about that. In a lower pitch as it moves away.
Okay, and that's the end of that. Now the thing about,
anything else out there?
well,
loudness, intensity.
should we talk about loudness? Well, it's like clap your hands right in front of the camera. Clap them again. It's not as loud here because that expanding bubble stretches the energy across a larger surface, so it gets quieter. So there's two things going on. The most important thing about the Doppler effect is the pitch change, the frequency change. But loudness is always also changing.
Yeah, the closer you get to that
different mechanism.
Object, is it the object or is it whatever that moving object, the louder it's
Now let's go on to the next thing.
Two waves can occupy the same point in space at the same time. This is called interference.
And we played with a little slinky. We might do that again today to show that.
When waves interfere, their amplitudes add algebraically, positive and negative. Okay. When a crest meets a crest, or a trough meets a trough, constructive interference occurs, so they add together.
You want to show them that over here?
Yeah,
You want to get on one end and
Yeah.
I'll get on the other.
I'll go this side right here. Okay. So we're gonna go to the right side. Ready?
Okay.
1, 2, 3. Boom. 1, 2, 3. Okay.
See, when you send a single pulse, they go down there like this. But if we both, on your mark, get set, go. When they get to the middle, you get the big bump.
Boom. Okay.
And that's called constructive.
Oh, sorry,
that's
I changed it.
constructive interference.
That's this one right here. Wrong way. There we go. Correct. Constructive interference.
You get a bigger bump. Remember this?
Bigger bump.
And then destructive interference.
That's when we've got our cancellation. I'll go right, you go, you're right.
On your mark, get set, go. Okay, notice there's no big bump. On your mark, get set, go. When they get to the middle, on your mark, get set, go, they cancel each other out. And you get no bump.
No bump.
That's destructive interference.
So that's a crest and a trough, and constructive and a crest and a crest, trough and a trough. Okay, beats. Okay, beats occur when waves of slightly different frequencies interfere with each other. And that's when we get that, so the oscillating between constructive and destructive interference, and it makes that wah 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 sound, okay? Wah 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 wah. And that's all there is to it. Now you can, how fast the wah 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 wahs are depends on how close the frequencies are.
Yeah, yeah.
And
We're covering everything in sound really fast here.
yeah, we are. And so you can solve for that. You can do, it doesn't matter which frequency you
If
put
the
first.
frequencies are close together, you get wah, wah. And if they're farther apart, you get wah, 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 wah.
And so that beat frequency is what you can solve. You can find that using this equation.
Yeah, we demonstrated that when we went through it before. We ain't doing it now.
Okay, waves at a boundary. When a wave encounters a boundary between two media, some of it is reflected and some is transmitted.
For example, if I send a pulse to the back, when that pulse comes back to the front, when it gets here, some of it is transmitted through the string and some of it reflects back through the slinky.
Standing waves occur when incident waves interfere with reflected waves at exactly the right frequency. Do you want to demonstrate?
Want me
this
to do
thing?
that demonstration?
Yeah, you want to do it?
Yeah.
Here, and I'll hold this guy right here.
All right, so if I send one pulse, it goes down to the other end and comes back on the opposite side. It comes back inverted. And it goes back and forth many, many times. If I send a bunch of small pulses at exactly the right frequency, they go back and forth many times and they interfere with each other. And this is a standing wave. I've got waves going that way, waves coming this way. Notice you can't see them anymore. All you see is the algebraic sum of the interference. And here we get constructive interference, here we get destructive interference. And by the way, that destructive interference is at equilibrium.
Boom. Nailed it. Spring drop.
Drop.
Destructive interference produces the nodes at equilibrium. That's what Mr. Boykin was just pointing at.
Yeah.
Constructive interference produces the antinodes. Amplitude increases. That's where we've got those.
Yeah,
Antinodes,
the big
amplitude
bumps.
increases.
Antinode is a long word. It's like the big bump. Node has no in it. There's no movement at the antinode at the node.
Movement at the node. Okay. We're almost finished here. A resonator reflects waves back and forth at a particular
We
frequency.
just happen to have one here.
Okay. So here's a resonator, and so as I smack this here, we have the waves that are resonating back and forth at a particular frequency.
So you send a wave down to the open end and it reflects back and forth at a particular frequency. Hit that again. And here's a shorter one.
Length matters, right? Okay. So a closed pipe resonator, that's what we've got, one end open, one end closed, reflects with inversion from one end and without from the other.
Now inversion is like when I sent the pulse down on the top and it came back on the bottom.
And how do we think about our wavelengths in here? Well, there is a quarter of a wavelength there is a quarter of a wavelength between a node and an antinode. Shall I do this on here if I can? Okay, so here, this is a wavelength between here and here, right, Mr. Boykin?
That's one wavelength, yeah.
Right here, okay. So we said there's a quarter of a length between a node and an antinode. So here's a node. So if I'm looking right here.
There's a node, there's an antinode, there's a node.
1, 2, right? So here's the 1 quarter, the 2nd quarter, this is the 3rd quarter, and that's the 4th one, right? So between here and here, there's just 1 quarter.
So there's a quarter of a wave
So that's like
between a node and an antinode. And on your pipe, you have a node at one end and an antinode at the other end. And so
there's a quarter of a wavelength in here. And the loudest sound from a closed pipe resonator is a quarter wavelength. So this is what we call our fundamental frequency.
Yep.
Now, if a closed pipe resonator has a quarter of a wavelength in it, how long is the whole wave? Well, it's just 4 times whatever the length of this is.
Yep.
So if this was,
Let's say it was 0.25.
yeah, 0.25. That's
It's a quarter of a meter.
If this is 0.25 meters, the whole thing would be a meter.
1 meter, that's right.
Okay, good call, Mr. Boykin.
Yeah.
I'm like, okay. Okay, so an open pipe resonator is the same at both ends. So either both closed or both open.
Well, slap it and keep your hand on there.
Yeah, so.
No, just like you did before. Keep
Yeah.
keep your, there you go. There's a, see how our hand closes one end. Now slap it and immediately take. Oh.
Right, so now it's a little bit different, okay? So the open pipe, I forgot how we did that. It's been a while. An open pipe resonator is the same at both ends. How much of a wave will fit in it?
Well, if it's the same, it's going to have the same parts of a standing wave. It'd be like a node and another node. And how much of a wave is between a node and a node?
Well, 1/2.
It's half a wavelength.
Okay. All right, so
So you've got a half a wavelength in an open pipe.
so that means the fundamental frequency of an open pipe resonator is 1/2 the wavelength.
So how long would the whole wave be?
Well, if this was, again, 0.25 meters, the whole wave would be 0.5 meters.
Yes, ma'am.
Boom. And that's it.
Ba-boom.